Hello everyone, and welcome to a new Unity tutorial about Scriptable Objects. In this episode, we're going to see how this amazing tool makes it easy to store custom data types, share information inside and across scenes, and even abstract away some of your code to help the game designers in your team tweak and improve the gameplay without having to deal with actual scripting. Of course, as usual, don't forget that you can get all of the code and assets we make in this video in the GitHub repo with all my Unity tutorials over here. And with that said, let's dive in and discuss the basics of Scriptable Objects. Scriptable Objects are a special type of data containers that make it easy to save large amounts of data in self-contained and efficient project asset files. Basically, they let us define our custom data types by specifying the data structure as a C# class, and then instantiate this class as many times as we need to get real usable data sources. These scriptable objects are very nice from a user perspective because they offer a clear and beginner-friendly edit UI directly inside the Unity Inspector panel. So once the data structure has been coded up, then anyone in the team can go ahead and refine the values of a specific data instance, which is great for non-coders gameplay artists. In the end, a scriptable object is therefore the combo of a C# structure on the one hand, and one or more asset instances on the other hand. These instances are always up to date with the latest value because they are automatically reserialized by Unity whenever the values change. Note that this does mean you have to set up serializable fields in your C# data structure, so you should either make your fields public or make them private but give them the serialized field attribute. One of the big advantages of scriptable objects is that they are obviously a great way to reduce data redundancy. Typically, if you have some enemies you want to spawn in your game that are all of the same type and therefore share some common attributes, for example the maximum health, the move speed, the attack range, etc., then it's interesting to use a scriptable object to define this abstract data, and have each instance point to it to get the values. In comparison, storing the data directly in the instance implies copying the same values over and over, which incurs a lot of data redundancy. Scriptable objects avoid that issue and instead centralize everything in one place to facilitate updates and redistribution of this data to all the interested parties. That's because a key idea when using scriptable objects is that of the single source of truth. To better understand this concept, let's see a typical use case for scriptable objects: the sharing of some data between multiple objects in the same scene. Now, it's true that one of the big recommended design principles among Unity game devs is to separate your codebase into several logical chunks, each in one script, and then spread these scripts on your different objects in a scene. This helps with what's called the separation of concerns, which is a crucial concept that, in a nutshell, means you try to limit as much as possible the reach of each script and have every script do a scoped and well-defined thing. That's a great design principle because it makes the codebase easier to browse, it helps with collaborative development, and in the best case, it makes for nicely decoupled systems that all live on their own and don't have any strong dependencies. But this last point is actually pretty hard to achieve in practice. Indeed, although chopping down your code in multiple scripts is super easy to do, actually decoupling the logic and making each script self-contained is way harder. Think of all the times where you've needed to access another object in your scene and you've done a get component on it. These are cases where you've coded strong dependencies and entanglement, because your script A cannot work properly if this dependency to script B or component C isn't available. Now, you might wonder if it's really an issue. After all, if your scene is built as expected, everything will work smoothly, right? Well, the problem is actually that any modifications to the script or one of its dependencies implies you'll need to update another part of the codebase. This, in turn, severely hinders collaborative dev, because if multiple devs work at the same time on the codebase, there will likely be conflicts. And finally, you can't easily extract a single system in your game to develop it and test it in a vacuum. As soon as you start to add the scripts of this system in a new scene, its strong dependencies will force you to basically re-import the rest of the game as well. All of this is pretty bad, and that's why it's usually nice to aim for as much decoupling as possible between all different game systems. And there are of course various techniques to do so, depending on the type of link you have between your scripts or your script and data. But here we'll focus on the case of maintaining and sharing data between scripts, because that's actually one of the strengths of Scriptable Objects. They make it quite straightforward to share data between multiple objects and keep everything centralized in a single place to avoid inconsistencies. So they're a great alternative to a pretty common pattern where you declare some static or global variables in a dedicated C# class, or you create singletons and game-wide references that live throughout the session and get updated over and over again from different points. This pattern is nice because it's quick to code, but it can sometimes get hard to keep track of. With Scriptable Objects, you can create an asset in your Unity project that is readable and editable via the inspector, thanks to a clear UI, and that your scripts can then reference to access the data and use or update it. This tool is therefore a great way to sanitize and organize your project's abstract data. Now, to better understand how they work, let's see a basic example of how to share data inside a Unity scene using Scriptable Objects. I'm going to use this little scene I prepared, where in the middle I've got my Viking hero, and you see that at the bottom I've got some UI elements. Namely, I've got a health bar on the left and a label displaying the current amount of experience of my hero. My goal here will be to store this amount of experience and the health data in a Scriptable object and have my UI manager read from this data source to always keep the visuals consistent with the data values. To start off, we need to create a new Scriptable object-based custom data type to define the two properties we want to store for our hero, the XP and the health. To do this, all we have to do is create a new C# script in the project, and then inside, declare a C# class that inherits from the Unity engine.Scriptable object class. Then in my class, I can list the properties as public variables to have them be automatically serialized when needed. Also, be very careful because your C# class name, in my case player data, has to be exactly the same as your file name, otherwise it won't work. Okay, now this C# code is the data structure of our custom type, so now we need to actually use this blueprint to make data instances. Because remember that what we want is a data container with actual values, not just an abstract structure like this. Typically, in my example, I want to actually store somewhere that my player currently has 0 XP and 100 health points. And then I want to be able to update this container with new values as the game runs. The trick to this is to add a specific attribute to a class, the createAssetMenu attribute, to specify a path to a new menu item in the creation context menu. If I save this and recompile, you'll see that now, when I right-click in the project doc and go to the Create menu, I have a new submenu matching the path I've just defined, and I can click this final item to instantiate the class as a new asset in the project. I can name it just like any other resource, and I then get direct access to the properties I defined earlier in the inspector. Of course, this is just one data instance, and we could easily duplicate it or create another one from scratch to store another set of values. For example, if we had multiple players, or if we wanted to test a specific scenario with some pre-initialized XP and health values. All of these assets share the same structure because they are all instances of our player data Scriptable object class, but each asset has its own specific values. Then the next step is to use this data in our game, and that's where Scriptable objects really shine. Basically, to read from or write to a Scriptable object, you just need to make a reference to it in a C# script, and then you can get and set its public fields just like with any other C# class. Except the data is directly serialized, and it is stored in this asset so we can modify it quickly in the Unity editor via the inspector, or any other script can point to it at the same time and see the changes reflected immediately. So let's see how this can help in our case to display the data stored in our player data instance at runtime in the game interface. I've actually already prepared a simple UI manager that I put on my UI object in the scene, and if we open it, we see that at the moment, it's displaying some hard-coded data with 10 XP and a health of 50 out of 100. But of course, we wanted to load the info from our player data asset instead. So we're going to expose a reference for a player data instance with a public variable, and then in the inspector, we'll drag in our data instance. Then in the script, we'll simply replace these hard-coded values with reads of the XP and health fields in our player data variable. Now let's edit our player data instance and set our player's info to some specific values. And if we run the game now, we see that when the script starts, it indeed goes to read the contents of our player data scriptable object and updates the UI accordingly. The only problem is that if we change the values in our scriptable object now, the UI doesn't refresh. If I exit the game, my data remains because it has been serialized, but it won't be reread by the UI manager script until the next time I start my game. That's because for now, my C# logic only checks the values inside the scriptable object in its start function. To solve this issue, a nice technique is to use events. These ensure that we remain very loosely coupled, because we can emit an event even if there is no listener for it, but it will also allow us to react to changes in the data instance very easily. So let's go back to our player data script and add a new Unity event field inside it, called updated. Note that we have to import the Unity engine.events package to use this variable type. We can also give our property the hide-in-inspector attribute because we don't want it to show in the inspector, it's just for internal use via C#. And now we're going to use the onEnable and onValidate hooks that we inherit from the Scriptable Object class to run some code when the instance is first set up and when any of its properties are changed in the inspector. Again, you see that Scriptable Objects are really cool because they're actually boosted data containers. They also encompass some logic thanks to these C# lifecycle hooks. But anyway, here I'm going to prepare my updated event in the onEnable function, and then whenever a property of my object changes in the inspector, its onValidate method will be called, and I'll invoke my event to propagate this notification. Finally, in my UI manager, I can set up a listener for this event that uses the updateDataDisplay as a callback function, and here we are. If we rerun the game now, we see that the data is initialized upon start like before, and then when I modify a value in my scriptable object via the inspector, the UI automatically updates to reflect this change. So that's really cool, we can actually control our UI in-game via the asset file in our project. But guess what? We can also use another script to write our data and still have these updates done via the code trigger a UI refresh. For example, let's add some test buttons in the top left corner to either simulate a hit and decrease the health of our hero, or give him some arbitrary quantity of experience points. I'm going to link those buttons to callbacks in another C# script that I've called Player Manager, and in this script I'll once again expose a reference to a player data instance and drag my asset to the slot. Of course, be sure to actually link the same asset, otherwise the data won't be synced up. And that's it! We can now restart our game, and if we click the buttons, the scriptable object updates, and the UI is modified immediately to catch up with the changes. So that's really cool! We can now totally control our player stats, either by hand or via code, and we notify all the interested systems of these changes thanks to events, so that they can react to the changes and run their own logic on their own, such as a UI refresh for the UI manager. Now, just as a bonus, there's a little improvement we can make to our player data class, and that's adding some value checks on the health parameter so that it doesn't get out of the valid range, which I've decided is between 0 and 100 so that it matches my UI health bar display. To enforce that the health stays in this specific range of values, we can do two complementary things. First, to avoid users inputting invalid values via the assets inspector, we can add a range attribute to our property. This will show the field as a slider that cannot go below the minimum or over the maximum, and so it directly reclaims the input to the proper range. Second, to also avoid coders setting wrong values from their scripts, for example our player manager that sets the health to a decreased value when we click the HP- button, we can transform our simple health member into an actual property with a getter and a setter. We just link it to a companion private member that we have to serialize so it is actually saved in the scriptable object, and then we use simple conditions to check if the new value is valid, or else bring it back to the right range. And there we go, we now have a nice slider in our inspector that makes it really easy to tweak the health value, and if we happen to reach 0 when clicking on the HP- button during runtime, we see that the value stays in the 0-100 range. So this simple example has showed us how scriptable objects are an amazing technique for decoupling our systems inside a scene and getting easy to read and easy to modify local data containers with some nice extra features like C# lifecycle hooks. Now time to continue our journey and explore another possible application of scriptable objects: the storage of session-wide persistent data. Indeed, another very common use of scriptable objects is to store project-wide, or at least session-wide data. If you've ever had to implement persistent data in your games, you might have come across the don't destroy unload function. That's a method that you can add to a script on any of your game objects to have them survive after a scene change. That's very nice when you want to keep the actual game object with its transform and update function, but when it's just about passing on data, this is a bit overkill and inefficient. Rather, here we can rely on a scriptable object to keep our data neatly organized and yet persistent across scenes. Don't forget that because it is serialized on disk, the data doesn't get discarded during runtime, or when you exit play mode for that matter. Any changes that are done to a scriptable object in edit mode or at runtime in the Unity editor are saved and remembered, which means that you don't risk losing your modifications and you can use the scriptable object asset as a global data source for the entire session or even the project. Typically, it's quite common in games to have some global settings with things like sound volume, music mute, or screen resolution. Those are properties that aren't linked to a specific part of the game, to any scene. Instead, they should be read and edited globally so as to stay consistent everywhere. This is a very good use case for scriptable objects. We just need to make a scriptable object script with our properties and then instantiate it in our project. And now this asset can be accessed and modified from various places and centralizes the data so that it is always up to date, consistent, and without useless redundancy. As explained in this very nice Unity tutorial video, scriptable objects can thus be used for many things. For example, persistent audio channels, or event-based scene changes that can be triggered when a player enters an area. Those two examples could definitely help with playing sounds during scene transitions or loading up scene chunks for an open world. However, it is important to remember that this data persistence does not transfer to game builds. It's only within the Unity editor. In a game build, you'll be able to get your current values from the scriptable objects, meaning the data they contain at the time of the build, but then they won't update and save modified values in the build version, because they won't be re-serialized. So if you need to get session-wide data in your build games, you'll need to rely on more manual techniques, like binary serialization or JSON and XML files, for example. If you're curious about this, I've actually wrote a few articles on that topic that I'll put in the description, so be sure to check that out. Anyway, for now, let's focus on using scriptable objects inside the Unity editor. Another cool thing is that, because as we saw in the previous section, using a scriptable object is as easy as dragging a reference to a script slot, you can very quickly switch between various data instances. For example, suppose you have a network manager script that you feed with some network settings data saved as a scriptable object. Then you could make a dev version, a staging version, and a production version of the data to easily define the right parameters depending on your current execution context. And switching between versions is just about dragging in the right asset. This last point actually brings us to another neat thing about scriptable objects, which is that when well integrated in your project and used from early on, they can be one of the core elements of a data-driven philosophy and push forward a no-code setup for your game project. So let's see why in more details. Okay, to wrap up this tutorial, I want to go one step further and discuss how scriptable objects can help us implement data-driven games, and abstract away the logic so that even non-coders in the team can tweak and improve the gameplay. So far, we've seen that we have to do some C# coding to define the data structure of our player data, and also for the different managers that interact with our data instance. This is great if you're into scripting, and it does make it fast to set up, but what if you don't code at all? Can scriptable objects still be useful? Well, actually, yes. By adding some preliminary steps on the dev side, we can also use scriptable objects to make a sort of basic visual scripting system for our game entities. Now, I do need to put quotation marks here, because we are not going to make some bold equivalent, or a true equivalent to C# scripting. But we can actually use the power of scriptable objects to represent some core data logic bricks, and then assemble these bricks together to form more complex systems, all inside the editor and just dragging about asset files. Consider our player data structure. At the moment, it is composed of two integer properties, the XP and the health. But now, what if we need to add some mana amount as well? With our current setup, we would need to come back to the C# data structure script and add the field, which would be another integer value. So in this case, another possibility is to not bundle all the data like this as a single player data structure, but rather create a basic unit brick, the integer variable, as a script object class, which just contains an int value property. And then we can instantiate this integer variable blueprint 3 times for our player XP, player health, and player mana values. You see that the nice thing is that this other organization would allow any non-coder in the team to very easily add new int properties to a player's stats, just by creating a new integer variable instance. And of course we could make some float variable, bool variable, string variable and more to handle other common variable types. Then by setting up some extra options, such as range checks on these core bricks, we could replicate our previous player data structure exactly, but in a more flexible way. Now, of course, this does imply you would have more asset files to handle in your project, and you still need the devs to prepare some actual C# scripts to read from these data instances and use the values inside at runtime to fit the game state. But again, we could prepare in advance some pretty abstract and one-size-fits-all mini C# classes, and we would implement a very basic fixed logic inside that would result in different outcomes based on the data we provide it with. With this new setup, building our logic would be about properly compositing and linking together all the little scoped pieces so as to create our actual behavior. So this alternative organization system might sound more complex at first, but once you've prepared all the core data bricks and the mini C# classes, it actually allows for lots of adaptability and agility in your project, and it lets the game artist in your team directly contribute to the construction of the gameplay experience in a completely no-code fashion. Anyway, with all that said, that's it for today. I hope you enjoyed this tutorial and that you've learned a few things to storing your data efficiently using Unity's scriptable objects. If you did, feel free to like the video and subscribe to the channel. And of course, if you have other ideas of Unity tricks that you'd like to learn, don't hesitate to leave a comment. As always, thanks a lot for watching, and take care.